Welcome to the second part of the OpenCL lectures of this course. The topic of this part is GPU architecture. We will take a more in-depth look on the hardware at the hardware of GPUs. The question is why is this important? Why do we even care? Can't we just use OpenCL? Actually, it is important to know about the underlying device architecture of the GPU. This is the way we can achieve the highest performance possible if we know about what the hardware does, how it's built, how the memory works on the GPU, so we can exploit it to be efficient. We will look at how the OpenCL specification that I've covered in the last part of slides, maps to the many core hardware. That means to the AMD GPU architecture, the NVIDIA GPU architecture, which is slightly different, and the cell broadband engine, although we'll probably skip this part since it's not extremely relevant to the course topics. And finally I will cover some OpenCL specific topics. The OpenCL compilation system and the installable client driver model, which I briefly mentioned in the previous slides. As I said, why is it important to look at vendor-specific hardware if OpenCL is platform independent? You need to gain intuition of how programs, loops and data need to map to OpenCL kernels in order to obtain performance. In short, what does the hardware do if you write a platform independent OpenCL program? You can also use this knowledge to observe similarities and differences between NVIDIA and AMD hardware. And understanding that hardware will allow for platform-specific tuning of code and generally writing efficient programs later on in the lectures. Before we look at graphics cards, GPUs, let's look at conventional CPU architecture. On a CPU that is found in a usual PC, you have a lot of space on that chip devoted to control logic instead of ALU. ALU is the arithmetic logic unit, the part of the chips that actually performs the computation, the arithmetic instructions, addition, multiplication, bit shift, etc. Control logic is responsible for handling multiple threads, as whenever your PC runs, when you have an operating system running and some applications, you have multiple threads, and these threads are managed by the CPU. And CPUs are particularly optimized to minimize the latency of a single thread. So no single thread may be stalled for a long time. That also means the CPU can efficiently handle control flow intensive workloads. Also, the CPU has multiple level caches that are used to hide latency. So multiple levels of memory that is quite fast to make it look like there is less latency for each single thread. Also, there's a limited number of registers due to the smaller number of active threads. By smaller, I mean smaller compared to GPUs. While there may still be a lot of concurrently active threads in a CPU, it is still much less than the thousands of threads that run on a GPU. Also, this control logic of the CPU can reorder the execution of different instructions in a program, provide ILP, that means instruction level parallelism. A GPU can find out whether some instructions in a program are independent and can be performed in parallel. And also, generally, this control logic minimizes pipeline stalls. I will come back to pipelines later in this part of the slides. The modern GPU architecture looks a bit different. We have on a graphics card a generic many-core GPUs. GPU. That means on a graphics card you do not just have one processor or four, but a couple, dozens. There is less space devoted to control logic and caches. Control logic is not so important because even though there are a huge number of threads, thousands, even then these threads work pretty much the same, and it is not of such importance if there is latency for them. Also, there are large register files to support multiple thread contexts, so the switching between threads, between many threads, can be made easier. The GPU has low latency hardware managed thread switching, and this is really important, a large number of ALUs per core with small user managed cache per core. So the most space that is devoted to chips on a GPU is for the ALUs, for the actual computations. So graphics cards want to do a lot of computations in some frame of time and not guarantee that one particular thread is really fast or every thread has low latency. So the memory bus that serves the GPU cores, is optimized for bandwidth. You want to get a lot of data processed in some certain amount of time. And it is not important if individual threads have a bit of a higher latency. As an example, let's look at the AMD GPU Hardware Architecture. You do not have to know about the details or the numbers here by heart, but this is just to give you an idea what the GPU architecture looks like. So this example on the left here is the architecture of the AMD 5870 hardware. As these slides are a couple of years old, this is not the newest generation of graphics card hardware, but it doesn't matter too much. The essential basics of the architecture remain the same. This AMD 5870 has 20 SIMD, single instruction multiple data engines, and these contain several cores. One core again is made up of 16 so-called SIMD units, which process 5 multiply adds per functional unit, which results overall in 2.72 teraflops of single precision floating point operations and 544 gigaflops of double precision floating point. One such SIMD engine, of which there are 20 on the AMD GPU, consists of a set of so-called stream cores. These stream cores are arranged as a 5-way very long instruction word processor. That means this is a processor whose instructions can issue 5 scalar operations, as in addition, bit shift or something similar, can be issued in one instruction word. These scalar operations are executed on each of the processing elements. That means on each value of your input data array. And all the stream cores in this one compute unit execute the same VLEIW instruction. And now we come to a very important notion. The block or the number of work items that are executed together is called a so-called wavefront. This is a really important notion you need to remember. The number of threads that can be executed at the same time or are executed in the same time in parallel. For one SIMD engine, on the 5870 graphics card, this is 64. So 64 work items can be executed in parallel at the same time on one SIMD engine. How does this map to the AMD, to the OpenCL specification? In the previous slides I showed you this diagram describing the OpenCL specification, the distinction between compute devices, the host and compute units and processing elements. If you want to map this to AMD hardware, you can see individual work items execute on a single processing element. And one such processing element refers to a single VLIW core. Multiple work groups execute on one compute unit, and such a compute unit refers to one of the SIMD engines, of which there are 20 on the GPU of AMD. Let's look at the GPU AMD Memory Architecture. The SIMD engine that I mentioned before, the fastest memory it has is the so-called local data store and the registers, which are memories per memory per compute unit. There is also a level 1 cache, which only works for one compute unit, and a level 2 cache that can be shared between compute units. There are several paths that reach to reach the SIMD engine. There is one path which is faster but only works for 32-bit precision operations, and a different path which is used if there are double precision floating point operations like in 64 bits, and atomics. We will get to atomics later, what they do. So this memory model can be mapped or is mapped to the OpenCL memory model. A subset of the hardware memory that I've shown you here is exposed in OpenCL. So that means the local data share can be used as is exposed as local memory. So whenever you write local in your current OpenCL kernel, you use this local data share. You can share your data between items of a work group, and this is designed to increase performance. This local data share is quite fast. Also, private memory utilizes registers for each work item, and the constant memory utilizes the level 1 cache. There is some more to know about constant memory usage on the AMD GPU. That means essentially the constant memory declarations work only for the following access patterns on AMD GPUs. For instance, direct address patterns, which means for non-array constant values where the address is known initially, so just one value. Or same index patterns, which means that all work items reference the same constant address. Or globally scoped constant arrays. That means arrays that can use the cache due to their small size. If you have an array that is less than 16 kilobytes, it can be globally scoped and flagged as constant. Then again, the access is very fast. In all other cases, the memory is not cached and delivers the same performance as a global memory read, which means it gets slow.